In this chapter, we will learn how to calculate IV flow rates, and we will learn three different methods: the dimensional analysis method, the formula method, and the division factor method. As we learned in the last chapter, oftentimes we use an electronic infusion device, and most healthcare facilities do use these electronic health infusion devices. These are programmed in milliliters per hour. That makes it really easy because you just program, you set up your IV fluids, and then you program in your milliliters per hour, which is usually ordered by the physician. However, there may be some occasions when you will not be using an infusion device, and you will have to calculate an IV flow rate that has been ordered in milliliters per hour to drops per minute. Standard drip factor is another term that we use for the drops per minute of an IV tubing that's being used. And different IV tubings have different drip factors. They will be printed on the package label. And you'll use this to calculate your drip rate. Your IV tubing will come calibrated, and it will be marked on your package. Here's three different packages that are calibrated differently. You can see here the 10, which means 10 drops per milliliter. Here is 15 drops per milliliter, and I think this one says 60. I don't have my glasses on. The bottom two are macro drip tubing, calibrated at 10 and 15, and there's also another one at 20. Those are the typical macro drip tubing calibrations, and then your micro drip tubing is always 60 drops per milliliter. For those of you that are a little more visual, I like this diagram out of your book. These three are your macro drip calibrations, and then here is your micro drip calibration. And you can see that this is 10 drops per milliliter, so this is represented here as a 1 milliliter with the 10 drops in it, 15 drops per milliliter, and then 20 drops per milliliter. So in order for these different types of IV tubings, in order to deliver 1 milliliter, you have to have the 10 drops, the 15 drops, the 20 drops, or on the microset, the 60 drops. When you're calculating IV flow rates, they may vary 1 to 2 drops per minute depending on how you round. Wait until the end of the calculation before you round. You will have to round up or down because here is a drop. Is it possible to give half of a drop? No. The answer is no. So you have to round because drops you're always going to have to round to the nearest whole drop. I believe I just said that. Okay, so we will look at dimensional analysis first. You're going to notice that one difference is we're involving two values because we're going to be looking for drops per minute. Whereas in other dimensional analysis problems, we were looking for milliliters or tablets or possibly units. When we're talking about IV calculations, we will be looking for drops per minute. So already it differs just a little bit because we will start our equation like that. So if we're going to use dimensional analysis, we're going to set it up like we've always set it up, except we're going to be using the two values. So for this one, calculating IV fluids at 125 milliliters per hour using tubing calibrated at 10 drops per milliliter, we want to put on the left side of the equal sign drops per minute equals. And there it is again. Drops per minute is what we will be looking for in this equation. Step 2 in dimensional analysis is to enter your drop factor. That's what we'll call this. This is the drop factor that you find on your package, which is 10 drops per 1 milliliter. Now, in keeping with our DA process, the next numerator is going to have to match this milliliters. So we're going to add the 125 milliliters per 1 hour. Then, because we want our final answer to be in minutes, we have to do a conversion here. This is our conversion step. So our hour and our hour have to match up there. So 1 hour equals 60 minutes. And then we're ready to calculate. So we can cancel out our milliliters, cancel out our hours, and we're left with drops per minute. And then we multiply those out. And that leaves us with this. Now we could further cancel out our zeros here, which would leave us with 125 over 6 equals 20.8. Now, can we give 0.8 of a drop? Nope. So we would round that to 21 drops per minute. Here it is written out completely again. You start with what you want, which is your drops per minute, and you set it up just like you do your other dimensional analysis. 10 drops per milliliter, so your drop factor goes here. And then your milliliter per hour. Then convert your hours to minutes. Cancel out your hours and your milliliters, and you're left with drops per minute. Next, we'll move on to the formula method. The formula method is used for small volumes to infuse in less than 60 minutes. It's especially helpful if you have an order that might say to infuse, let's just say 60 milliliters over 30 minutes. So that small amount of time can be plugged into here. And you can use your formula method for that. Now this makes sense because think about it. the flow rate method, or the formula method, says flow rate equals milliliters per hour, so your volume, times your set calibration, which remember is your drops per milliliter. So what you're getting when you take your volume that you want to infuse times your drops per milliliter is your total drops needed for that volume, and dividing it by the time, which would give you your drops per minute. So using the same problem that we used last time, let's set it up in the formula method. You've got your volume here, you've got your drop factor here, and you've got the time to infuse it here. 125 times 10 is 1250 over 60. You can calculate that out. You could actually cancel your zeros. You end up with 125 divided by 6, and you come up with the same answer that we did when we used dimensional analysis. The division factor method is very similar to the formula method, except you do one of the conversions. Basically, you memorize the division factor, and then you memorize those division factors using the constant of 60, because there's 60 minutes in an hour. Okay, so I told you that the typical drop factor sets are 10 drops per milliliter, 15, 20, those are your macro sets, and then your 60 drops per milliliter is your micro set. And so these would be the numbers that we would use, and you divide these into 60, and you come up with your division factor that you end up using. So let's look at it. It's easier if you work a problem. So using our constant of 60, because there's 60 minutes in an hour, dividing 10 into 60, you would always come up with 6. Dividing 15 into 60, you would always come up with 4. Dividing 20 into 60, you would always come up with 3. And of course, 60 into 60 would always be 1. Now I'm going to work a problem here, the problem that we've been using, doing the division factor, so you can actually see that what the division factor does is eliminates a step for you. So using the formula method, we had 125 milliliters to infuse over an hour. So let's put this out here. If we are using the 10 drops per milliliter, which we did in the last two examples, we would have 125 milliliters times 10 drops per milliliter over 60. And so what do we do here? Cancel out our 0, and what we end up having is 125 divided by 6. And so you can see that using the division factor is just taking your milliliters in hours and dividing it by the division factor, because 10 drops per milliliter is always going to be 6. And so it's just removing a step for you by learning what those division factors are, and then you just have to divide 125 by 6, and you come out with, of course, the same answer, 20.8 or 21. If we did it with the next one, 125, we use, say, this set, it would be 125 milliliters times 15 drops per milliliter, again over 60, that's our time. And so what would we be doing here? 15 goes into 60 4 times. So in essence, you end up dividing 125 by 4. And so you can see how we use that division factor. And 125 by 4 is going to be, I don't know, 30 something. And so because it takes more drops per milliliter for this particular drop set, our final drops per minute would be increased in order to deliver the 125 milliliters per hour. Now in the last slide I worked that out using the formula method so you could see that the division factor method is basically the same. It's just removing those steps because you already have reduced the fractions. So calculating an IV at 100 milliliters per hour using the set calibrated at 10 drops per milliliter, we know that for 10 drops per milliliter the division factor is 6 because 10 goes into 60 6 times, so it would be 100 divided by 6, and then you would have your answer, 16.7, which you cannot give 0.7 of a drop, so it would round up to 17 drops per minute. Now, on the micro drip set, you need to remember that when it's used, the flow rate in drops per minute is always going to be identical to the volume in milliliters per hour. So let's look at this and we'll see why. If we have 125 milliliters times 60, that's our drop factor, per milliliter, over 60, these are always going to cancel out and leave you with 125 drops per minute. So when you're using a micro drop set, it will always end up being the same number as what your milliliters per hour, what that volume is. It's always going to be identical to that because these two cancel each other out. Okay, now once you have figured out how many drops per minute you need to give, then of course you have to count the drops in the drip chamber. The drip chamber, as you recall, is this. And remember I told you that we needed to only fill this half full so that we could count drops. Rather than stand there and count drops for a full minute, regulating the flow rate, you can divide your total number of drops by 4, and that will give you how many drops you need in 15 seconds. And so then, for example, with this one, you want a total IV drip rate of 100 drops per minute. You divide that by 4, and you need 25 drops per 15 seconds. And so that way you can watch this chamber for 15 seconds until you have 25 drops dropping into that drip chamber in 15 seconds, and then you know you have your 100 drops per minute calculated. Now sometimes we get off schedule with our IVs, and so say maybe it's stopped for we give medications, and so the main IV gets off, or various reasons why we may get off schedule. You can increase the rate, and we'll talk more about that in the next chapter, but a couple of things that you need to consider when you are increasing a rate to compensate for running behind is the type of fluid that's being infused. If we were infusing a medication such as insulin, we would probably not want to increase that rate. Some cardiac drugs, we would want to be very careful about increasing the rate because of the effect on the patient. If it's just regular maintenance fluids, then that's not as much of an issue, but we do want to look at the individual's ability to tolerate an increased rate. If they have kidney problems or congestive heart failure, they might have difficulty tolerating an increased rate. So, to get it back on schedule, we need to look at our patient and the types of fluid that are being infused before we just automatically increase an IV rate. Make sure you know what your clinical facility's policy is on correcting off-schedule IV rates. Most clinical facilities will have a policy regarding that. And then you're going to recalculate your flow rate using the remaining volume and the remaining time you have to infuse that. As I mentioned before, there'd be certain medications and IV fluids that you would not want to increase the rate. Some of them are listed here. And then whether you're increasing or decreasing a rate to get the IV back on schedule, you want to closely monitor the patient for effects of the rate change. So let me show you how to work one of those if we are recalculating. Let's say that we have an IV of 1,000 milliliters that was ordered to infuse over 10 hours. And it was to go at a rate of 25 drops per minute. The set calibration is 15 drops per milliliter. And after 5 hours, the total that has infused is 650 milliliters. Should have been half of 1,000 in 5 hours, so it should have been 500 milliliters. So what we're going to have to do is recalculate a new drop per minute for the flow rate to complete the infusion on schedule. So your time remaining, we've got 10 hours was our original order, minus 5 hours equals 5 hours. Our volume remaining is 1,000 milliliters minus what's already infused, which is our 650. And that leaves us with 350 milliliters. And so what we want that to go in over is the remaining 5 hours. So we would take our 350 divided by our 5 hours equals 70 milliliters per hour. Our set calibration for 15 milliliters, our division factor for 15 milliliters is what? 60 divided by 15 is 4. So what would we need to do? We would take our 70 divided by 4 equals 17.5. We can't give half of a drop, so we'd need to slow our IV rate down to 18 drops per minute in order to complete this in the ordered amount of time. And it would be the same way if we were speeding it up. We would follow this same progression of calculations.